Welcome to the world of structural analysis. In this opening scene, we'll introduce the core idea behind structural analysis, understanding how structures like buildings and bridges stand up to various forces. Structural analysis is a fundamental part of civil engineering, ensuring that everything from skyscrapers to small homes remains safe and stable. By examining how loads and forces interact with different materials and shapes, engineers can predict how structures will behave under real-world conditions. This knowledge is essential for designing safe, efficient, and economical structures. Let's begin our journey by exploring the basic concepts and importance of structural analysis. Structural analysis has a rich history, evolving alongside human civilization. Early builders relied on intuition and experience, but as structures grew more complex, a scientific approach became necessary. The development of mathematics and physics allowed engineers to better predict how structures would behave. Over centuries, new materials and construction techniques have shaped the field, leading to the sophisticated analysis methods we use today. Understanding this evolution helps us appreciate the importance of structural analysis in modern engineering. Why do we need structural analysis? The answer is safety and reliability. Every structure must withstand various forces such as weight, wind, and earthquakes. By analyzing structures, engineers can identify potential weaknesses and ensure that buildings, bridges, and other constructions won't fail unexpectedly. This process helps prevent disasters and saves lives. It also allows for efficient use of materials, reducing costs and environmental impact. Structural analysis is the backbone of safe and sustainable construction. Structures come in many forms, from simple beams to complex skyscrapers. In structural analysis, we categorize structures based on their function and design. Common types include buildings, bridges, towers, and dams. Each type has unique challenges and requires different analysis techniques. For example, a bridge must handle moving loads, while a building must resist wind and earthquakes. Understanding these differences is key to choosing the right analysis method for each project. The heart of structural analysis are loads and forces. Loads are the weights and pressures that structures must support, including the building's own weight, people, furniture, wind, and even earthquakes. Forces are the effects these loads create, such as tension, compression, and bending. Engineers must carefully calculate these to ensure structures remain stable and safe. Understanding loads and forces is the first step in analyzing any structure. Loads are generally classified into three main types: dead loads, live loads, and environmental loads. Dead loads are permanent, like the weight of the structure itself. Live loads are temporary, such as people or furniture. Environmental loads include wind, snow, and earthquakes. Each type of load affects structures differently, and engineers must consider all of them during analysis to ensure safety and performance. Choice of materials plays a crucial role in structural analysis. Different materials like steel, concrete, and wood have unique properties that affect how they respond to loads and forces. For example, steel is strong in tension while concrete excels in compression. Understanding material behavior helps engineers select the right material for each part of a structure, ensuring both safety and efficiency. Structures are made up of basic elements like beams, columns, slabs, and trusses. Each element serves a specific function. Beams support loads over spans, columns carry vertical loads, slabs provide flat surfaces, and trusses offer strength with minimal material. Understanding these elements and how they interact is essential for analyzing and designing safe structures. Key concept in structural analysis is equilibrium. For a structure to be stable, all forces and moments acting on it must balance. This means the structure won't move or collapse under load. Engineers use equilibrium equations to analyze forces and ensure stability. Mastering this concept is fundamental for anyone studying structural analysis. Some structures can be analyzed using only the equations of equilibrium. These are called statically determinate structures. Their internal forces and reactions can be found directly, making analysis straightforward. Examples include simple beams and trusses. Understanding these structures provides a foundation for more complex analysis methods. Other structures are more complex and can't be solved with equilibrium equations alone. These are statically indeterminate structures. They require additional methods like compatibility equations to analyze. While more challenging, these structures are common in real-world engineering because they offer greater strength and redundancy. There are several methods for analyzing structures, including the force method, displacement method, and computer-based techniques. The force method focuses on balancing forces, while the displacement method looks at how structures deform. Modern engineers often use software to handle complex calculations, making analysis faster and more accurate. Modeling is a vital part of structural analysis. Engineers create simplified models of real structures to predict how they'll behave under different loads. These models use assumptions to make calculations manageable but must still accurately represent the structure's behavior. Good modeling is key to reliable analysis results. When loads are applied, structures deform. Deflection is the movement of a point on a structure, while deformation refers to changes in shape. Engineers must limit deflections to ensure comfort and safety. Excessive movement can cause damage or discomfort even if the structure doesn't fail. Analyzing deflection is a key part of structural analysis. Stress is the internal force per unit area within a material, while strain is the deformation caused by stress. These concepts help engineers understand how materials respond to loads. By analyzing stress and strain, we can ensure materials are used within their safe limits, preventing failure and prolonging the life of structures. Structures can fail in different ways, such as bending, buckling, or breaking. Understanding these failure modes helps engineers design structures that avoid them. For example, slender columns may buckle under load while beams might bend or crack. Recognizing potential failures is crucial for safe design. To ensure safety, engineers use a factor of safety in their designs. This means structures are designed to withstand loads greater than those expected in use. The factor of safety accounts for uncertainties in materials, loads, and construction. It's a critical part of structural analysis, providing a margin for unexpected events. Structural analysis must follow building codes and standards. These regulations set minimum requirements for safety, materials, and design. By adhering to codes, engineers ensure their structures meet legal and safety expectations. Codes are regularly updated to reflect new knowledge and technology. Technology has revolutionized structural analysis. Advanced software allows engineers to model complex structures and analyze them quickly and accurately. Tools like finite element analysis make it possible to predict behavior under a wide range of conditions. Technology continues to push the boundaries of what's possible in structural engineering. Modern structural analysis also considers sustainability. Engineers aim to design structures that use resources efficiently and minimize environmental impact. This includes choosing eco-friendly materials, optimizing designs, and considering the structure's entire lifecycle. Sustainable analysis is becoming increasingly important in today's world. Summary: structural analysis is a vital part of engineering, ensuring that structures are safe, efficient, and sustainable. As technology advances, new methods and materials will continue to shape the field. Future trends include greater use of automation, smart materials, and integrated design processes. By mastering the basics of structural analysis, you're building a foundation for a successful career in engineering.